in this section, we're going to graph sine and cosine functions. And the idea of where the graphs come from are kind of an unknown secret in trigonometry. So I'm going to do my best to show you where the graphs come from. And then once you have sort of memorized the shape of a couple of the graphs, it's pretty easy to adapt them to whatever you want. So in essence, this graph of the sine of x comes from the unit circle. So in the unit circle, we have 0 degrees, 90, 180, and 270, and 360. And then we know that the sine of theta is equal to the y value on the unit circle. The reason that's the case is in a right triangle, if this is theta, then sine would be opposite divided by hypotenuse. So when theta is 30 degrees, for instance, then the length of the opposite side is half as big as the length of the hypotenuse. So it could be 1 and 2, could be 8 and 16, but at 30 degrees, the length of the opposite side is exactly half as big as the length of the hypotenuse. And that's true for every right triangle with a 30-degree angle. Okay? Well, if that's true, if the sine of 30 is equal to 1/2, then the size of the triangle is not important. Right? So we decide to make a triangle that's easier than all others. And we know that the sine of theta is opposite over hypotenuse. But I can simplify this equation a little bit if I make the hypotenuse length 1. So your hypotenuse of a right triangle is 78.3 feet. That's okay. We just call it 1. 1 what? Well, it turns out to be 1 radian eventually, but we just say it's 1 hypotenuse. And when we do that, we end up with, so when this is equal to 1, I get the opposite divided by 1, which is simply opposite, which is where the unit circle comes from. The unit circle has a radius of 1. And the nice thing about that is, when I draw this 30-degree triangle, so there's 30 degrees, then the coordinate is √3/2, 1/2. And I don't think anybody picked up on this when we have been working on the unit circle this year, but we know that the sine of theta is equal to the y value. Right triangle trig says the sine of theta should be the y value divided by the hypotenuse. But the hypotenuse is length 1, so we don't need to do that. Okay? Now, I'm not sure if that made any sense, but that's why we use a unit circle. And the beauty is, whatever circle you have, you just throw out the units and you call it 1 radius, which turns into 1 radian, and we'll get to that in just a minute. So, how do we graph the sine function? Well, the sine of theta is equal to y, which is an angle, this is an angle, which spits out a ratio. And if my calculator is in degrees, which it is, I can say the sine of 30 is 0.5. Whoa, were you here the whole time? Oh, okay. It scared me. So that means whenever theta is 30 degrees, the opposite side is half as big as the hypotenuse. If I make the angle bigger, the sine of, say, 45, now the opposite side is 70% as long as the hypotenuse. If I make the angle smaller, the sine of 15, now it's 26%. And every angle is linked to a ratio. And in the last chapter, we remembered that this ratio cannot be bigger than 1. We talked about how the sine of theta cannot equal 1.5. Why was that? It's bigger than 1, and that's a problem because, let me help you out. Right. Can opposite divided by hypotenuse be equal to 1.5 over 1? No. Why not? Hypotenuse is always the biggest side. So we learned that the sine of theta has to be sandwiched between 1 and, in the unit circle, -1. It can never be bigger than that, because the opposite side can never be bigger than the hypotenuse. There are a couple cases where they're the same size, at 90 degrees and at 270. So the sine function has a percentage that is linked to every single possible angle. And I've shown you 3 of them on my calculator. 15 degrees, 30 degrees, and 45 degrees. The graph of the sine function simply represents every single ratio. And once again, the beauty of the unit circle is they're all there as y values. So we are going to link how big is the y value on the unit circle as theta gets bigger. So I'm going to draw a graph. Okay. My x-axis is going to actually be a theta axis, which is the angle of the unit circle. And then my y-axis is going to be the y-axis that is the same value as the unit circle. So I'm going to start at 0 degrees. And if you remember back to my unit circle lesson 2 years ago, if you had me, we called it the height of the wall. So the sine value is actually how tall the graph is for that angle. At 0 degrees, how tall is the wall? 0%. The y value at 0 degrees is 0. Okay? And then as that angle rotates around, as it comes in this direction, the wall starts to get a little bit taller and taller and taller until at 90 degrees, what is the value of y? 1. 1 what? 1 radius. At 0 degrees, the y value is equal to the radius of the circle. And eventually we turn that into radians. So I know that the graph is going to be bound between 1 and -1, and it will never leave those bounds as long as I don't transform the graph at all. So I start marking off degrees, and over here at 90 degrees, the height of the wall is 1. And then I have this series of y values, and I can take each one of those and link it to that appropriate degree measure. That make sense? Once I spin past 90 degrees, what happens to my y values? What happens to the y values as I spin down through quadrant 2? They start to get shorter until at 180 degrees, the height of the wall is 0. So over here at 180, the graph's going to look like this. Does everybody understand that? Okay. Now, once I spin past 180, what do you notice about the y values? They're negative. So at at 270, I'm actually down at -1, and the graph looks like that. And then over at 360, so as the wall gets taller and taller and taller, it maxes out at 270, and then the wall starts to get shorter and shorter and shorter until at 360 we are once again at 0. Do I have to stop there? No. I could keep spinning. So once I hit 360, Then I could do 361, 360, 370, 380, until I get to 450. And at 450, once again, I have a value of 1. So it's pretty easy to understand that this graph is going to continue, and the sine function looks like this. And actually, it's infinite in either direction. Does anybody not understand that? There is a major misconception here. Some people look at the sine graph and think, oh, it's just halves or semicircles. It's half a circle and then a negative version of half of a circle and then a positive version of half a circle, and that's not the case. In fact, in a circle, so if I had a semicircle like this, this point of the circle is actually straight up and down. And this point of the circle is actually straight up and down. The sine function doesn't come anywhere near that, right? Right here, that slope is actually 1 over 1. It's the slope of 1, up 1 over 1. Okay? So a sine graph never gets steeper than 1. So basically, if you were driving a car up this hill and down, when you got here, you would be falling straight down. In a sine graph, if you're driving a car, this right here would be a 45-degree angle. And you're never steeper than that in the sine graph. So they actually should look a little bit more like this, but I just didn't draw it very well. Okay, cosine is similar, but instead of graphing the y values, we're going to graph the x values. At 0 degrees, I've made a mess of this, but at 0 degrees, how big is the x value? It's at 1. So the cosine graph starts at 1, and then at 90 degrees, so right here, how big is the x value? 0. So the sine and the cosines use the same lengths. They just kind of present them in a different order. So the cosine graph looks like this. And then that will repeat forever and ever. Now notice, if you grab the cosine and pull it 90 degrees to the right, it will perfectly match up with the sine graph. So in general, the sine of theta looks like this. We have our 4 important points, which are 90, 180, 270, and 360. And the sine graph bounces between 1 and -1, and it looks like this. And can you see that that really doesn't look like 2 circle halves anymore? That graph is a better rendition. Okay. The cosine of theta is similar. It still bounces between 1 and -1, and it still has the same 4 important points, but it starts at 1 and looks like this. Okay. But I've lied to you a little bit because we can't really graph angles on the x-axis. In order for this graph to be representative of its true shape, we need to know how far to mark the x-axis. I just kind of guessed and said 90 degrees is about that far. But how far is a degree in inches? The answer is a degree is not inches. A degree is a rotation. So if I rotate from here to here, that's 1 degree. Right? 1 second on a clock is, what would that be, 10 degrees? No. 360 divided by 60 would be a 60th. Anyway, whatever. So instead of graphing these in degrees, we actually graph them in radians. The definition of a radian is, instead of measuring the rotation, we're going to measure how far the tip of the dial spins. And when the tip of the dial spins, or sorry, the tip of the dial travels such that the distance covered by the tip is equal to the radius, we call that 1 radian, which is hard to remember because we don't really use that very much. So instead, uh-oh, I've broken it. Wow, just chopped a book in half with my headphone wires. So instead of degrees, we graph these in radians. So this is pi over 2, pi, 3 pi over 2, and 2 pi. Okay. All right. If we look at a trig function, it's going to repeat itself over and over and over. And these are called periodic functions. You guys live in the electronic age, so you don't really know what periodicals are, but magazines and newspapers are called periodicals. Well, we can chop this graph into pieces that are identical, that contain a full cycle. So from here to here represents one cycle. Cycle, there we go. Sure. And one cycle is called a period. Now, I don't think you're going to have to think too hard to remember that. Period is what we call a cycle, something that happens over and over and over, right? That's where it came from. So that is a mathematical term. Aren't you so excited you learned that today? And periods are defined by length. The period of the sine and the cosine graph is 2 pi. That's how long it takes to do one full cycle. If you start at 0 degrees and you go all the way around the circle, you complete a full cycle in 2 pi. But we can change the graph and alter the period. So if I said, what is the sine of 2 theta? Well, this says instead of moving around the circle at theta, at the rate of theta, we are going to spin around the circle twice as fast as you were before. Okay? So I'm going to spin around this circle twice as fast. I'm going to input theta values, and then I will graph the values that are twice as big. So when I try to graph the sine of 45, I actually times that by 2, and that creates the sine of 90. So where 45 is, I am going to graph the value of 90. So hold on, let me get rid of this. So my normal sine graph looks like this. And here's 45 degrees. So where 45 degrees is on the x-axis, I am going to graph the value of 90 degrees. So when I turn my dial this far, I'm going to graph the number associated with a spin that's twice as big. So I'm going to graph 1. So right here. And then when I plug in 90, I'm going to graph the answer at 180. So that would be here, and then here, and then here. And what do you notice about that sine function? If I spin twice as fast, what happens to the period? It's half as long. How long does it take me to do a full cycle? Well, it only takes me half as much time as it would have before because I'm spinning twice as fast. Okay, so the normal points would be pi over 2, pi, 3 pi over 2, and 2 pi. When I spin twice as fast, what is this point? Well, it's half of this. What's half of pi over 2? Pi over 4. And then this is still pi over 2, but what's this point? Well, there's a little bit of a trick. If this is 1/4, then this would be 2/4, which is 1/2, and this would be 3/4, and then this would be 4/4, which is pi. Okay, who doesn't understand that? Probably just want to see another one. Okay, let me try another one. What about the cosine of theta over 4? What happens to my rotation if I divide theta by 4? It takes 4 times as long to get around the circle. When you plug in 80, you actually put the number in for 20. When you plug in 180, you actually plug in the number for 45. So it's going to take you 4 full revolutions to create one cycle. The normal cosine graph looks like this. I'm not going to have enough room, sorry. Make it smaller. So the normal cosine graph looks like this. But if I am dividing my angles by 4, I'm going 4 times as slow. So I kind of need to create 4 of these. And now my cosine graph is going to go from here to here to here to here to here. So my period, period is now 8 pi. Because this is 2 pi, this is 4 pi, 6 pi, and 8 pi. And the period is easy to figure out. The equation for the period, if I have the sine of A times theta, the period is 2 pi divided by, that's a 9, divided by A. So whatever number is inside here, all you do is take 2 pi and divide it by that number. So in this case, we divide by 1/4. 2 divided by 1/4 is 8. So that full cycle takes place over 8 pi radians. Okay. What happens if I want to graph the negative sine of theta? What does that tell me to do? Flip it. But we have 2 choices. Am I spinning the dial backwards, or am I changing the sign of the y values? And it depends if it happens inside or outside. Stuff on the inside affects theta, which are angles. Stuff on the outside affects y values. So this basically says, take the height for that angle and then make it negative. So the graph would look like this. A negative on the outside. A negative on the inside would flip the graph this way, which you probably aren't going to see. Okay. What about this? So I'm multiplying something by 3. Am I multiplying the angle by 3 or the heights by 3? The heights. So the regular cosine graph looks like this. And those heights came from the unit circle. And now I make him 3 times taller. So 1, 2, 3, like that. So there are 3 transformations we're going to do. One is put a negative on the outside. That flips things upside down. Put a number on the inside. That changes the period. In physics, you call it the frequency. Right? How often do you bounce up and down? In mathematics, we usually look at period, which is how long is one cycle. In physics, that's called wavelength. They actually do both. Right? What is the length of a single wave? And then putting a number on the outside changes what we call the amplitude, which is how high does the graph reach. So let's take our base graphs of the sine of theta, which looks like this, and then the cosine of theta, which looks like this. And remember, we have these 4 sort of important points, and those points are pi over 2, pi, 3 pi over 2, and 2 pi. And then we're going to graph other functions that have just been transformed. So if I said 4 sine of 3 theta, what would that look like? Well, it is 4 times as tall as the original sine graph, and the dial is spinning 3 times faster than it does normally, which is going to shrink the frequency. Okay, so now I graph this 1, 2, 3, 4, 1, 2, 3, 4, and it used to take me 90 degrees to reach the top, but now I'm traveling 3 times faster. So how long will it take me to reach the top? 30 degrees. But we don't ever graph in degrees, we graph in radians. So if it took me pi over 2 to make it to the top, how do I get there 3 times faster? Pi over 6. Good job. Pi over 6. Okay. All right. How long is it going to take me to get back to 0? Well, if the first segment is pi over 6, the next segment is also pi over 6, and pi over 6 plus pi over 6 is 2 pi over 6, which simplifies to be pi over 3. Okay, what's the next one going to be? So 3 pi over 6, which becomes pi over 2. Okay, and then this one would have to be, so we have 1, 2, 3, 4 sixths, which is 2 pi over 3. Now, if you don't understand that, there's another way to do it. If this point here is 2 pi, then going 3 times as fast, it would have to be 2 pi over 3. And then you can just create half of this is 1/3, and half of 1/3 is 1/6. I think it kind of depends on the problem. It would be good if you knew how to do both, but it doesn't. It will always work both ways. Okay. All right. What about this? Negative 1/3 cosine of theta over 2. What can you tell me about this graph right off the bat? It's upside down, and it's 1/3 as tall. So the original cosine graph is stuck between 1 and -1. Those are kind of the upper and lower bounds. But it's a 2, divided by 2. Yeah. So this graph is going to be stuck between 1/3 and -1/3. So it's going to look like this. So this one, oh wait, it flipped, didn't it? You guys are just going to let me make a mistake. There we go. Now we have to figure out those critical points. Oops, right there. So how long is it going to take me to get to here if I'm traveling twice as slow? Twice as long as pi over 2, which is 2 pi over 2, which is pi. And then this point used to be pi, but I'm going twice as slow, so it's 2 pi. And then this point used to be 3 pi over 2, but now I'm going twice as slow, so it's 6 pi over 2, which is 3 pi. And then this would be 2 pi times 2, which is 4 pi. Now, if you wanted to do it the other way around, that's fine. You say the normal rotation creates a period of 2 pi. I double that, and I get 4 pi. So I put 4 pi at the end. So halfway would be 2 pi. Cut that in half, and I get pi. 2 pi plus 1 pi is 3 pi. All right. I believe that's everything you need. All right. Get to work.